Okay, so I promised today that I would talk about the relationship between asymptotic Hodge theory and degenerate Hodge theory. So I'm going to start with the degenerate Hodge theory. So if I have a degeneration of algebraic varieties at the center of a disk and a variation of Hodge structure leading up to that on the punctured disk, how can I relate the two structures, one at the center and the asymptotic one? So I'm going to start with what you get at the center when you have a singular variety. When we have a smooth projective variety, remember we had an associated polarized Hodge structure to it, where the sum of the PQ parts, you have PQ decomposition of cohomology, where P plus Q is equal to the degree of cohomology that you're considering, n, right? Well, that's not going to be true when you have a singular variety. Instead, you have some singularity locus, and there's going to be some pieces with P plus Q less than n associated to the smaller and smaller singularity strap. If we were doing non-compact varieties, then there would be P plus Q greater than n pieces as well. But I'm going to stick mainly to singular compact varieties. So what is a mixed Hodge structure? Well, before we had just a single Hodge filtration. So we had a Q vector space, which I'm now going to want to be defined over Z. So this is a free abelian group of finite rank, no torsion. And then we have a decreasing filtration on its complexification. That's your Hodge filtration. But now there's a third ingredient, which is that there is an increasing filtration on VQ. So it's just naked V will be the Q vector space, is this tensor Q. And what criteria make it into a mixed Hodge structure? We have to have that if I take the graded pieces with respect to the weight filtration of the Q vector space, together with the Hodge filtration restricted to these graded pieces, complexifications, then this is a weight n Hodge structure for each n.
Right, the weight filtration is defined over Q, or I don't see it.
So this is Z, is it? This is defined, this is sort of the name for the whole thing, but V itself, if I just write V, I could mean the whole thing, or I could mean just the Q vector space. Okay, it's the same thing. So this is, I'm taking the weight graded pieces of the Q vector space.
But I still don't understand. So the weight filtration is defined over Z, or
no. You can define it over Z, but that's not, you won't get an abelian category that way. And mathematicians hate it if you don't have an abelian category. So you want the weight filtration to be on Q. And this will be very natural later because the thing that produces the weight filtration is not defined over Z, which would be the monodromy one.
So when you say that, okay, like when you include VZ as part of the data, do you mean that you include a lattice?
This is the lattice. I include that as part of the data, yes. Okay. That will be important for constructing extension classes. So this is sum U, and UC is the direct sum over P plus Q equals N into PQ parts. And then remember that we had FK of UC is the direct sum of UP N minus P, where P is greater than or equal to K. Let me clarify something here. Negative P and Q are allowed. Negative weight is allowed. That thing that Jacopo said yesterday about Hodge structures have positive weight is bullshit. Okay, no one thinks that in Hodge theory. Okay, so negative P and Q are allowed. We want these U's, these graded pieces, to be polarizable on their own, meaning that you can take a sub-Hodge structure of this, and then it has a complement, an orthogonal complement. Okay, what is amorphism? Because we're going to have maps between mixed Hodge structures. Amorphism is going to be amorphism of the underlying free abelian groups from V to V prime, such that it respects the two filtrations. So MQ, U tensor Q, applied to W gives
to
W
be
prime.
free.
Okay, it could be torsion, but
I mean, you want
that's
an
gonna be-
abelian category.
what?
You want an abelian category.
Oh yeah, of course. Sorry. Thank you. Yeah, so I shouldn't insist that that's a free abelian group, but in my mind, in all the examples, it will be. Okay, UQ of W is contained in W prime, and UC of F is contained in F prime. Okay, so it respects the two gradings, and then there's an important bigrading that comes out of this, which is kind of, if you're new to mixed Hodge structures, this is extremely helpful because it allows you to see mixed Hodge structures as a decomposition into PQ pieces, which without this you don't get. Okay, so this says that VC has a unique decomposition into a direct sum over P and Q of PQ parts, such that three things are true. The first is that FKVC is equal to the direct sum over P and Q and C with P greater than or equal to K of the VPQs. The second says that weight L VC is the direct sum over all P and Q and Z with P plus Q less than or equal to L of VPQ. Okay, so you think of the weight as sort of the sum of P and Q, the Hodge filtration as sort of this P and bigger than that P, bigger than P bigger than or equal to L to K, and then finally that VQP bar. Well, ideally we would want VQP bar to be VPQ, but that's not true. So you have to go modulo the direct sum over all A less than 0 and B less than 0 of VAB. And then that's as good as you can do. And indeed, these three things uniquely specify the VPQ decomposition. There is a formula for the VPQs. It's disgusting and you don't want me to write it down. It serves no one. Okay, so then we have Hodge-Delene numbers. These are simply the dimensions of the VPQs. And I can make a nice little diagram. Put P in that direction and Q in that direction. And I'm going to plot those PQs such that HPQ is not equal to 0. So maybe you might have a mixed Hodge structure that looks like this. Okay, so that's mostly pure of weight 3, except I have a weight 2 piece because 1 plus 1 is equal to 2. And this is exactly the kind of mixed Hodge structure you have if you have a family of 1, 2, 2, 1 Calabi-Yau threefolds and you allow it to acquire a single node. Then this is the mixed Hodge structure that the singular fiber, the conifold fiber, will have. Yes.
Sorry, shouldn't it be P plus A, Q plus B in this modulo relation? That's all.
Yes.
Or A smaller than
A smaller than P and B smaller than Q. Sorry, I was thinking in terms of Lie algebra. Sorry. Not writing what I have on my page. Okay. So yeah, please stop me if you see something wrong.
But
I haven't
why
had
do you
enough
require this
coffee.
modulo relation?
What is what?
Why do you require this modulo?
Because otherwise you, it's impossible to have it without the modular. Going modulus. Okay. A mixed Hodge structure is called R split if you actually have equality, and that's a very special kind of mixed Hodge structure. Okay, so these things I call usually Hodge-Delene diagrams. They're very useful. In some contexts, you want to move the picture up or down by, 1, 1 or -1, -1. So there's something called a tape twist. Twist is when you append an R with parentheses to a V, and then that means B of R, PQ is defined to be VP plus R, Q plus R. So that has the effect of pushing the diagram down by minus R minus R. Okay. That shifts the picture. All right, so here's a real example. First simple example. Let's consider mixed Hodge structures of this type. So this would be our F1, and this would be our weight 0. And that's sort of all of the information. How do these two filtrations play against each other? You can have a basis subordinate to the weight filtration, which is weight 2 and weight 0, or you can have a basis subordinate to the Hodge filtration, which is F0, F1. And then you can compare those two bases. It's the comparison between these two bases expressed by a 2x2 matrix, which is the entire data on the mixed Hodge structure. So the way this looks is we have a morphism of mixed Hodge structures from this bullet here, which is called Z of 0, because it's trivial rank 1 mixed Hodge structure of type 0, 0. And then there's a piece here, which is clearly of weight 2 and type 1, 1. That's called Z of negative 1, according to this tape twist fiction. Negative 1 shifts you up by 1, 1. And so in the middle, we have our V. V has a morphism to this bullet by passing to grade weight 2, and weight 0 injects into V. And so this is a short exact sequence, meaning this map is injective, this map is surjective, and the kernel of this one is equal to the edge of this one. So we can say 1 in here goes to some element we'll call gamma naught here. And we can say that typically when you append an R, you think formally of also multiplying the Q structure by 2 pi I to the R. So I would write here 1 over 2 pi I as the generator of this set of minus 1. And then there's an element gamma 1 in the center going to it that is defined over Z. And then I say, well, I want to compare that with the Hodge basis or with the Hodge filtration. So that will be generated by some omega. And I can write omega in terms of gamma 1 and gamma 9. And the information comparing the two bases, I'm not even going to write the second basis element subordinate to Hodge decomposition, is given by this A. In fact, A naturally lives in C modulo 2 pi I Z, and this is the obstruction to splitting the mixed Hodge structure. In other words, getting a morphism of mixed Hodge structures this way, whose composition with this is the identity. So X1 of MHS Z of minus 1 by Z of 0 is isomorphic to this, and this A describes the mixed Hodge structure up to isomorphism.
But if could you mention what the notation Z0 and Z, I mean, Z some integer means? Yeah.
Right. So Z of R, I'm identifying with 2 pi I to the R Z. And this has to do with the way that these twists and the shifts of the according shifts of the mixed Hodge structure appear in the context of taking residues of differential forms. And when you take residues of differential forms, there's always an S1 that you integrate around dz over z, and that produces a 2 pi I. Okay, I don't want to go too formal.
Sorry. Yes. So when A would be 0, then the mixed Hodge structure would just be a direct sum of pure Hodge.
Yeah, that's right. So I mean, I don't want to formally talk about like what is an extension, but let me just give the idea here. You can take a lift. So this Z of minus 1 is simultaneously integral, but it is also in F0 of itself. Sorry, F1 itself. So I can either try to lift this to something integral, which I already did, or I can try to lift it to something that remains Hodge but is not integral. So I would call this, say, F1. And now I can take the difference of gamma 1 and F1, and that will go to 0. And so it will come from something here. And that something here is essentially your A over 2 pi I gamma naught. And so that tells you the instruction to choosing these two lifts to be the same thing, which is what's required to get them out. Okay. So that's the idea of why that's the extension class. So what does this have to do with geometry? Suppose I have the following sort of degenerate variety. All right, what is that? That's a degenerated genus 2 curve. I've allowed a genus 2 curve to acquire a node. I can resolve singularities of this like so. Okay, so now I have Q1 and Q2 going to a point P. I'm going to call this thing X tilde and this thing X. So I have a resolution of singularities there. I have here the inclusion of P, and here the inclusion of Q1, disjoint union Q2. And when I have this kind of square here, where these two things are isomorphic outside of the inclusion of these two things for a resolution of singularities, this gives me a long exact sequence in the cohomology of the corresponding variety. So I would start with H1 of X goes to H1 of X tilde plus H1 of P, which is 0, so I omit it, goes to H1 of this, which is also 0, so I omit it. And then on the left, this thing has to come from H naught of this, modulo H naught of these. That can be sort of summarized as H naught of P. And really, I can think of this as a Z of 0, which is generated by the difference of these 2 points. Okay. And I'll point out also that this is just an elliptic curve, so I might as well call this E. So I have an extension of H1 of an elliptic curve. H1 curve. Right. I have a 1, 0 class, a 0, 1 class, it's weight 1. And that's being extended by a Z of 0, which is the difference of points, Q1 minus Q2.
Yes, can you explain again where does this sequence come from?
Right, so I have a resolution of singularities. Here I've included the singular set. This is the preimage of the singular set under this resolution of singularities. And when you have a square like this, you could call it a Meyer-Vietoris square or something like that, then there's an exact sequence going from HK of this to the direct sum of HK of these, to HK of this, to HK plus 1, to HK plus 1, to HK plus 1, and so on and so forth. And that's an exact sequence of mixed Hodge structures. Okay? And so that gives us, in this case, the extension that we would like to know whether it's split, whether it's actually seeing geometry. And in fact, the extension class here, epsilon, in X1 MHS of H1 of E by 0, you always write the right-hand term first. This is isomorphic to, up to duality, the Jacobian of H1 of E, which is, again, essentially just E itself, C. You can think of this as group law on E, and indeed, Abel Jacobi of Q1 minus Q2, again, not worrying about signs, this gives my class here. Okay. So if I look at the difference of these 2 points in the group law as a point in E, regarded as a point in its Jacobian, then that's really the extension class of this mixed Hodge structure. So the mixed Hodge structure is capturing for you some of the geometry of what has happened under this degeneration. Okay. As another example, I might mention.
Can I ask something?
Yeah.
Is there something special if the elliptic curve is special, like if it's a CM elliptic curve? Can you say something?
If it's a CM elliptic curve, then you would have interesting automorphisms, right? And so I suppose it's possible that maybe you have some action that works down here and up here, and maybe that would tell you something, that would reduce in some way the possibilities for this Abel-Jacobi image. But I mean,
There's no arithmetic condition on the extension curve.
Not exactly. I mean, the place where a CM elliptic curve would really do something for you is if the CM elliptic curve was itself a tail in some extension, which is something, or is it the tail in the semi-stable replacement for a degeneration? And that would happen for a family of surfaces. So that's a bit more complicated. It can be important, but not in this case. Okay, so here's another sort of example you could have. I already mentioned that if you have a family of 1, 1, 1, 1 Calabi-Yau threefolds, and it has a place where it acquires a conifold point, a node, then the resulting mixed Hodge structure of the conifold Calabi-Yau will have a 3-0 part, a 0-3 part, and a 1-1 part. So that's the form its mixed Hodge structure will take. And here's one more little interesting example. Suppose I have a degeneration of K3s, right? You could have K3s acquiring what's called an E6 tilde singularity. And then you do something called the semi-stable replacement for that. And you get something called the Tyranny Generation. So the following is a very common thing that can happen for K3s. It's also known as a type 2 Kulikov degeneration. You have a del Pezzo surface, say cubic surface, like what I wrote here, and then some other surface here, and they meet along an elliptic curve, okay? And this gives rise to an exact sequence of the form H1 of E goes to H, let's call this whole thing X, H2 of X goes to H2 of Y direct sum H2 of del Pezzo, H2 of curve. And let me just assume for simplicity that Y is P2. Usually wouldn't happen, but I'm just, so that this knocks this out. And I'm left with the del Pezzo, the cubic surface, whose cohomology is Z of -1 to the 7. Then I could quotient out this and this by a hydroplane class. And I end up with an extension of Z of -1 to the direct sum 6 extended by some mixed Hodge structure, and here I have H1 of the elliptic curve. So what would this extension look like in one of these Hodge-Deligne diagrams? I have H1 of my elliptic curve, and I have 6 classes here. Okay, so this 6 means that H11 thing is 6. So what is the extension? How can I see it geometrically? Well, cubic surfaces have 27 lines, right? That's a beautiful piece of algebraic geometry. Take any 2 of these lines. Look at where they meet E. Take this Q1 minus this Q2. And then this extension, the extension is captured by Abel-Jacobis of Q1 minus Q2 again. Except you get Abel-Jacobi of lots of Q1 minus Q2s, and it's going to give a point in the E6. So I'll just put a dot there. By looking at various lines and how they intersect the elliptic curve and taking differences of them, you have to organize the information properly, but you will get a point in E6. Okay.
Can you say again what is this diagram? So this is a Calabi-Yau threefold.
Yeah, so this is a conifold Calabi-Yau, and I haven't said anything about what this extension would be.
And
It's
what
a
is
little
this
more
111? It stands for being in complete intersection of.
So 1111 Calabi-Yau threefold means these are its Hodge numbers. H30, H21, H12, and H03. So this is the kind of Calabi-Yau that occurs in a 1-parameter family, and you'll have like a typically a special point where this is the cohomology of the fiber, a singular fiber of this type. What you can do is you can resolve this, and then the resolution of singularities produces a P1 cross P1, and you can take the difference of rulings on that, plus and minus, and that's an algebraic 1 cycle. And that thing has an Abel-Jacobi image and the Jacobian of this weight 3 Hodge structure. And that's actually the extension class in this case. So all of it's very geometric. It's capturing geometric information. But we'd like to be able to capture this information asymptotically without worrying about the singular geometry, with just starting with a variation of Hodge structure given by essentially a D-module differential equation on a punctured disk. And somehow that differential equation should know about this, okay, without actually constructing the singular geometry. That's part of the strength of these methods.
By the way, is there characterization of mixed Hodge structures in terms of co-characters?
Yes, there is. That's not so well known. You can indeed take co-characters. So what you have to do is you have to consider GM cross GM over C. So Z comma W, and then you take Z comma W to Z of the PW of the Q, essentially. And that gives a bi-co-character into GC, which is your group of automorphisms of V preserving Q. And then you can take the Q closure of the image of that homomorphism, and that will give sort of the Hodge group of this mixed Hodge structure. So all of that stuff can be done for mixed Hodge structures too. Okay, so now let me tell you about degenerations and asymptotics, and then connect the two.
Sorry, can I make a comment? So
Sure.
So you somehow use two different notations for the same notation for two different things, right? So there's this HPQ up there, which are the dimensions of the disease splitting, right?
Yes.
And on the other side of the board, you use the H as the Hodge numbers of the Calaria threefold. So when you write
Well,
1, 1, 1,
yeah,
1,
okay, so maybe this should be H generic,
yeah,
something like that.
so one should not
Right.
confuse that there.
Right,
the
and so
picture
then,
is-
then these are the actual things I'm calling HV. Okay. So what is a unipotent degeneration? Remember, we had the notion of a variation of Hodge structure, and that consisted of what? It consisted of a local system, Q local system, which one could take to have an underlying Z structure, and what usually does. And then we have V tensor O. Think of this as chief of sections of a holomorphic vector bundle, or just as a holomorphic vector bundle, and then a flag of holomorphic subbundles given by the Hodge filtrations on fibers. And then we have the connection, which is a flat connection, which simply kills the flat structure given by the local system. Then we have this pairing, Q, the polarization. So this will be a polarized variation of Hodge structure over delta star. And then we had by the monodromy theorem, which the way I proved it is due to Borel, T equals T semi-simple times T unipotent. Well, these are commuting elements in our Lie group G. This is with T semi-simple finite. So this is the Jordan decomposition. The main result is that the eigenvalues of this are roots of unity. T semi-simple kappa is the identity, and T unipotent is unipotent. And I'm mostly going to care about the case where kappa is 1 and T semi-simple is trivial. That n is equal to log, just for now, let me say T unipotent, which means the following. And this is where you sort of see the problem with C as opposed to Q. Sum of -1 to the K minus 1 over K. I have to divide by K. T unipotent minus the identity to the K. That lives in N V Q, where as usual, V is a reference fiber over some S naught. Okay, and then we also have T unipotent is equal to EXP of N. All right. So now we want to extend across the disk, the whole disk, across the function. So how do we do that? It's a theorem that any holomorphic vector bundle over the punctured disk is actually trivial and extends across the whole disk. But how do we do that? How we do it matters. So Jameen tells us that there exists a canonical extension I don't mean an extension in the sense of extension classes, I mean an extension of V to the whole disk of the holomorphic vector bundle. So let's specialize the unipotent case. For simplicity, then we take gamma I to be a basis of the reference fiber. And remember that if I follow gamma I around the origin by this local system, it doesn't come back to itself. It comes back to itself twisted by T inverse, what I'm calling T inverse. Remember, there's a difference between T on the basis of the local system and T on a single valued object written with respect to that basis, the opposite. So I write gamma I tilde to be e to the log of s over 2 pi I n gamma I, and this is now single valued. It's no longer integral or rational, but it's single valued, and it's a holomorphic basis of V, and so it furnishes a basis for VE formally. You just extend VE by this thing. The point being that since as you go around the origin, T inverse operates on that, and as this goes around the origin, it gets increased by 1, so it gets changed to e to the n times the original. You have a T and T inverse, and these cancel as you go around the origin. Okay, so now if we write Fs dot with respect to gamma tilde, this replaces the period map associated with the variation, which is just telling me my flag in here, my Hodge flag in here, as I vary S in here. So remember, I can always lift this to universal cover, right? So this I'm going to call phi tilde. This replaces this. And remember what the coordinates are in here. I'm calling Z in here, and Z goes to E to the 2 pi I Z in here, which is S. And so going from S to Z is L of S. So that replaces this diagram by the following. Psi tilde of Z is defined to be e to the minus Zn phi tilde. Okay. You see, Z is L of S. So what I'm doing is I'm saying with the minus sign, because I'm writing now the single valued object with respect to this untwisted basis. Okay, that costs me an e to the minus L of S. And now this is going to look like a single valued family of matrices, right? Because now I'm expressing a single valued object with respect to a single valued object. I'm expressing a basis of the Hodge decomposition with respect to this single valued basis of the holomorphic vector bundle. And I claim, and I won't prove, the theorem of Schmidt, that psi extends across. So you see here, I had to go modulo the action of monodromy to get this phi. Here, because I've untwisted, and I'm writing single valued with respect to single valued, this lifts to here. Just delta star goes to D check. And so now this thing extends across the origin, and I set F infinity dot B psi C. A little more concretely, what is this? This is the limit as s goes to 0 of e to the minus L of s n fs dot. Remember, this is exactly what we had to do. This is exactly what we had to do yesterday to change the matrix, which was a 4x2 matrix, so that we didn't get something stupid in the limit, right? So we actually got something that captured that cross ratio that I was after when I had a genus 2 curve degenerating with 2 nodes to P1 with 2 pairs of points attached. Okay. So this is the thing that you have to compute. This is a little bit strange because here, if you think of this as being D in D check, then I started off with this nice phi of s. As s goes to the origin, I get some point in the boundary of D. Whereas now I'm replacing that by this untwisted gadget, psi. And now that could go to anything in D check. It could be in D, it could be outside of D. It's a completely different limit. But you see, sort of being constrained to be in the boundary means you're going to carry less information. Whereas being able to be in all of D check means you have, well, most of D check, means you have a lot more information that you might contain in that limit. So that is the abstract 30,000 foot view of what we did in that particular example yesterday.
So
yeah.
Is it fair to say that this theorem essentially says that you can always pull out the logarithms in, say, if you think more about period integrals, it means that you can pull out the logarithms which make them non-single valued, and then the remaining pieces are just holomorphic functions which you can extend to 0 because there's just no.
You're literally setting all the logarithms to 0. That's what you're doing. Of course, if you change the local coordinate, here's the tricky part. You change the local coordinate t to alpha s to alpha t, right? Then log of t becomes log of alpha plus log of s. So clearly setting s to 0 and setting t to 0 differs by a log of alpha. So the solution to this is that you kind of have to go modulo such changes in the limiting mixed Hodge structure, and people do. Unless you have very good reason to stick with a particular local coordinate, which if it's defined over Q and you want to preserve that aspect of the story, you do. Okay.
Could you repeat what D check was?
D check was the compact dual of my period domain. So this is the thing that's GC monoparabolic. This is the thing that's GR monocompact. Okay. So this is Hodge structures satisfying both Hodge-Riemann bilinear relations. This is Hodge flags satisfying only the first Hodge-Riemann bilinear relation. Okay, so again, to reiterate, simple example, if I have elliptic curve degenerating, like so, over disk, and maybe F1S generated by the class of a holomorphic 1 form. If I write it with respect to the duals of these 2 cycles, alpha check and beta check, I get something like F of S holomorphic, G of S plus L of S F of S, the logarithm part of the period, like Thomas was saying. And then what I do is I say F1 infinity is the limit as S goes to 0 of e to the minus L of S n, which is just 1, 1 minus L of S 0. And that's going to sort of limit of this applied to this vector here. And generated by this thing. So this will give me C of F of S, G of S. It is exactly as if I set L of S to 0. That's the effect. And I also need to, of course, take the limit as S goes to 0. So that does that. On the other hand, we had this naive limit, F1 lim, that just did not do this untwisting action first. And so L of S goes to infinity and dominates everything. And we end up with that. So that's in the boundary of the upper half plane in P1. as you can see, it's not as interesting as this. Because what this is telling me is, did I write it out this way? Okay, maybe I'll come to that in a moment. I'll leave some space here. Anyway, there's something called the associated nilpotent orbit as well that I should briefly mention. So if I have a limiting mixed Hodge, if I have, a limiting Hodge flag, getting ahead of myself, associated nilpotent orbit, which sort of captures this limit mix, what will be a limit mixed Hodge structure up to ambiguities in your coordinate change. Theta of z is e to the zn f. Okay, and this is a priori a map from the upper half plane to D. It again descends to a variation of Hodge structure, delta star to D modulo gamma, or P. And in this example here, what will that be? The resulting nilpotent orbit, F1 nilp S, will be generated by, what do? You take this limiting Hodge flag and you just retwist it by this. And so that has the effect of giving me F of 0, G of 0 plus L of S, F of 0. Okay, so this closely approximates the original variation of Hodge structure. Okay, very closely as you go towards the origin, but it's more trivial than the original variation of Hodge structure because it doesn't have these interesting holomorphic functions. Now on to what is the limiting mixed Hodge structure. Okay, since n is nilpotent, the basic lemma from theory of from linear algebra, right? That there exists a unique increasing filtration, W bullet V, such that NWK is contained in WK minus 2. I'm not writing the WKV, but it's implicit. And n to the k, applying it k times, gives me isomorphisms between grade weight n plus k v and grade weight n minus k.
Maybe you can repeat again what this GR means.
Okay, yeah, right.
You
So
wrote it down before.
grade weight A of V means weight A of V modulo weight A minus 1. Okay. So you can see where integral structures get a little bit tricky. You can do it, but you know, you would have to intersect this with VZ and intersect this with VZ. I take that quotient, you get a torsion. Okay, so this has to be true for all k. I guess in the traditional vector space lemma, you would center this filtration about 0. I've centered it about n because n is the weight of my Hodge structure. This is convenient. Okay. So Schmidt tells us, so specifically speaking, this thing about psi extending across the origin, or equivalently about the filtration of this, of that by holomorphic subbundles extending to the full punctured disk. This is a consequence of the nilpotent orbit theorem. What I'm about to say is the consequence of the SL2 orbit theorem. So V lim equals V F infinity W dot. So I use this filtration I just specified, the limiting Hodge filtration, decreasing filtration, and the reference fiber away from the origin. This is a mixed Hodge structure. And n V lim to V lim twisted by -1, means shifted up, is amorphism. Or mixed Hodge structure. Alternatively, you can think of n from v-lim to v-lim as being a -1 morphism. Okay. That's the way it's going to look in terms of the pictures. All right, so coming back to this picture over here, what does this say? V-lim looks like what? Well, remember I have for my untwisted classes, which I'm now evaluating at the origin, the monodromy logarithm is going to send this to beta and beta to 0. So I have a picture that looks like this, where here is my weight 0. It's generated by this class here. And I also care about what my F1 is. That's going to be generated by the limit of this omega s that we have here, which we've just conveniently written down here. So F1 is generated by omega 0 equals f of 0 alpha tilde check of 0 plus g of 0 beta tilde check. So that's the picture. You can also say that it's generated by this whole thing divided by f naught. So then that kills this and gives you g naught over f naught. And this is the previous, the thing we previously called a over 2 pi I. So if I consider 2 pi I g of 0 over f of 0, that's my extension class. So there's something about this sort of analytic leading term of the logarithmic period that this limiting mixed Hodge structure is capturing in its extension class. So that's very subtle information that it's getting its hands on. All right, so what do the Hodge-Deligne pictures for these limiting mixed Hodge structures look like? So a corollary here is if the limit is the limit mixed Hodge structure of a variation, so the limit phi delta star to period domain with Hodge numbers h modulo t, then writing h infinity pq for the dimensions of the VPQ limits. These are the Hodge-Deligne spaces for the limit mixed Hodge structure. We have the following three things. The sum in the vertical direction of the HPQ infinities equal the original HP n minus p's at the pure variation. So this is saying that the bullets in my picture can only move up and down. Okay, bullets move up and down. Okay, so this is true for all p. And then HPQ infinity equals HQP infinity, so it has the usual Hodge symmetry, but also they're symmetric. They're symmetric not just about this line, but about the line p plus q equals n. So this is also equal to n minus q, n minus q. So the points in general come in quartets like that. And then finally, HP minus 1, Q minus 1 infinity is less than or equal to HPQ infinity if P plus Q is less than or equal to N. So what this is saying is that as you approach this anti-diagonal, like so, the numbers are increasing. So the ranks of these spaces are increasing. What that's really telling you is that we have little N strings centered about this anti-diagonal line, okay, and which are also symmetric about the diagonal. So you should think of pictures like this, where N is sort of taking you along a string, okay? What this really reflects is that I have a representation of SL2R on this picture. And these pieces are isotypical, these N strings are isotypical components of the symmetric cars, the standard representation of SL2R. me just write down some possible pictures you can have. Examples with V, the delta star of weight 2 with original Hodge numbers H20 equals 1, H11 equals M, and H02 equals 1. Then the original mixed pure Hodge structure is 1M1 with this picture. This says that there's no degeneration, or that at worst the monodromy is finite. Okay, this we would call type 1. Finite monodromy. Type 2 is going to be where this last bullet moves up by 1. So we get something like this with n operating. Here's m minus 2. This has rank m minus 2. H11. That's type 2. This is these are Kulikov types, and this is Tyranny Degeneration. Sometimes language is used. And then finally, at sort of the maximal unipotent or large complex structure limit type degeneration, n is acting like this. Which means I should stop talking, right? Except I still need to.
White pieces or colored pieces?
White pieces.
There's a whole box.
There's a whole box. Okay, I think I can make do with this. Here's one more example of the possibilities. If V, I mean, how did I enumerate these? I just moved the bullets up and down in such a way that those three rules are satisfied. If that's true, then the limit mixed Hodge structure of that type exists. That's a theorem. You can see this. It's not hard. So if I have weight 3 variation with all Hodge numbers 1, then the limit mixed Hodge structure is one of 4 types. Either type, again, we can call it 1, not. Finite monodromy. I1 is conifold monodromy. Give you a limit mixed Hodge structure. It looks like this. It's type 2 naught, which looks like this. This is again sort of Tyranny degeneration. And then type 3 is where you have, or rather type 4. Skip 3 in this case. Okay. So those are the possibilities. And let me just remark that for Hodge structures of this type, well, the interesting extension is of this z of minus 3 by this z of 0. And what you always see in the variations of Hodge structure arising in mirror symmetry, which for 1, 1, 1, 1 variations come in sort of 14 hypergeometric flavors. This extension class always looks like zeta of 3 over 2 pi I cubed times some rational number q. And that rational number q knows the Euler class of the dual Calabi-Yau threefold in the sense of their symmetry of the A model. But the zeta of 3 is really remarkable. And trying to prove this without the aid of anything like mirror symmetry, trying to do it just by a complex analysis leads you into the land of something called motivic gamma functions, which has been the focus of some of my work for the past couple of years. Very neat stuff. It's invented by Golishev, Zagier, Bloch, and Mashalysik. So let me now say, we'll take 5 minutes more. In the case of a geometric degeneration, how do you connect geometric? Limit mixed Hodge structures to
What do you mean
mixed
by
Hodge structure.
non-geometric degeneration?
Well, I mean, the existence of the limit mixed Hodge structure and so forth, this is true for any degeneration, any variation of Hodge structure over a punctured disk.
Okay, so you're basically saying you may not be necessarily be able to interpret it geometrically.
Right, I mean, you could just start with a D modular or something, differential equation on which you have a variation of Hodge structure. But now let's assume it comes from geometry. Let's say I have a family over the punctured disk where this is a smooth projective morphism. And of course, I want to claim that I have some smooth total space for simplicity in this smooth total space with fiber x naught over 0 in here. And I'd like to connect the mixed Hodge structure here to the limit mixed Hodge structure over there. Right? There should be some, one would hope there's a connection. And as before, I'm going to write n for the monodromy logarithm. I'm assuming t is unipotent. Well, no, actually, let me not assume t is. And let me write hk lim of xt for the limit mixed Hodge structure on the kth cohomology on the left-hand side. Then there are two exact sequences. There's something called the Milner sequence and the Clemency sequence, which together give you a lot of power. Milner sequence basically starts from the long exact sequence of the pair given by the total space, which is deformation equivalent to x naught and xt. And when you write out the long exact cohomology sequence of these and do a bunch of manipulations, here's the sequence you get. You get something that goes from hk of x naught, this is a mixed Hodge structure on the singular variety, goes to hk lim of xt, goes to something, goes to hk plus 1 of x naught, and so on. I'll continue on your merry way. Now, what is this something? This something is called the vanishing cohomology. It vanished. But more seriously, it's a complicated thing to define. So you can use the theory of mixed Hodge modules to put a mixed Hodge module structure on the vanishing cycle perverse sheaf, which is a perverse sheaf supported on the singularities of x naught. And that gives some God-given mixed Hodge structure here. How do you compute it? Well, it turns out that there is some work that goes back to the 70s and to Josef Steenbrink about the spectrum of hypersurface singularities. And that can get you started. If you have a degeneration that has only hypersurface isolated singularities, or you can actually extend this to one parameter singularities with bad points in one parameter singularities, and calculate what this thing is in here. And it depends only on the singularity type. It's some mixed Hodge structure. And then once you know that, and maybe you know something about this, you can compute the asymptotic thing, which is the really important thing to compute in Hodge theory. You can also constrain this by the type of variation that degenerated to it. The Clemency sequence is a bit of a different beast. So I'm not going to write all of it, but let me just write a couple terms. So there's a Hodge structure on the homology of x naught, which I have to twist so it's in positive weights. And then I push this x naught forward into curly x and pull it back to x naught again to go into the cohomology of x naught. And then that goes to hk plus 1 lim of xt. And in fact, it surjects onto the t invariance of hk plus 1 lim of xt. So what this is telling you is that the t invariant part of limit mixed Hodge structure, which is the stuff that's at the bottom of all the n strings and invariant under the semi-simple t semi-simple, this finite thing, which acts by morphisms of mixed Hodge structure, everything, that all of the invariant stuff comes from the cohomology of the singular fiber. So that's why when you had like the conifold degeneration, limit mixed Hodge structure, you had inside this the mixed Hodge structure on the conifold fiber. That's just the invariance under monodromy, because this is n and monodromy is e to the n.
So the stuff at the bottom of the end strings is what you see in the actual H3 of the singular fiber. And that's the way it always is, according to this local invariant cycle. Okay, so I will stop there. Sorry to sort of end with blistering up.
Okay. Good.
Questions or comments? No?
So now if we want to kind of generally study what cycles shrink in a manifold, right?
Yes.
Kind of with this motivation of saying, I want to understand the distance conjecture, I want
Yes.
to understand what states become like. How far
Look at the stuff at the bottom of the non-trivial end strings.
how far is this technology in doing it? So you mentioned, you already gave some examples where it can be done, right? That you have created this very abstract classification. I think that this is completely general, right? Nothing dodgy there. But then how far are we in identifying exactly that for the Tyranny degeneration in the K3, this and this cycle shrinks by using the exact sequence?
Mm-hmm.
Well, I mean, it has to be, first of all, cycles that if you, I mean, there's a canonical map from the cohomology to the homology. Right? Because cohomology you want to think of topologically as cycles that kind of avoid the cycles. I'm being a little bit precise. But then those are clearly homology cycles, right? So if I have like something like this, then this is a cohomology cycle, right? It's non-trivial as a cohomology cycle, but as a homology cycle, it's trivial. So that's the stuff that's at the bottom of the end strings, right? Or, well, at least the stuff that's at the bottom of the end strings, right? Because this is sort of, all right, okay, I'm gonna say something not quite right.
But is this, do you have to know some extra things about, you have to know a lot about the geometry itself still, right? So you cannot, it's not clear that every singularity which you get from the Hodge theory point of view is actually realized in a Calabi-Yau manifold, which
Maybe we should have some ground rules for this discussion, one of which is we start with a semi-stable reduction, so that we're talking about sort of a nice normal crossing degeneration. So I think that will help. That's a first order approximation.
and then all of them are realized. Well, I know that all of these are realized, but what about more complicated situation of intersecting things?
I don't know exactly what you're asking. So.
Yeah, so if I look at, I want to have a clearer understanding how well this abstract picture is related to this geometric picture which you're describing.
Right.
And say in specific examples. And I want to understand, so to say, how well this is developed, this technology. Is that it's an example-based thing. So I cannot abstractly talk about the relation between these types and the types of curves or cycles shrinking in the market.
Well, then we should start with some sufficiently non-trivial examples. See if we can connect.
So in examples, this is done, right? This is also what you did. But it's not, there's no general theory of this, general abstract theory. Where you don't have to look at
I can answer that question when I have a better sense of exactly what.
Maybe related to this question. So I think if you just take as Hodge numbers 1, 100, 101, it's a very nasty example, probably, but so do you have a geometric realization guarantee that all the subtypes of singularities could come up with abstract? I think the question was also a little bit in that spirit. Because of course, for these ones, we have examples even in the 14 hypergeometric families, they are all realized.
Yeah. Right.
For physicists, this would be an important.
Well, I mean, it is true that you can geometrically realize all degenerations of abstract variations of Hodge structure. If all you care about is the types, you could do that simply by taking constructions that involve massive numbers of elliptic curves. It's very simple.
Yeah, okay. This might,
But Calavia threefold, honest to God, Calavia threefold.
Unless you got a Clavia threefold, it might be much harder.
Yeah.
Yeah.
It would be nice to, we call this sometimes like geometric engineering. It would be very nice to engineer.
You can't ask for too much. I mean, it's not even known like if every, I mean, there's a conjecture about which Hodge structures of type 1001 are motivic, but that's not.
So this is my question. So even the simple situations are not, it's not 100% clear which ones are realized in geometry. And if they are realized, it's not that we can build them like bottom up, right? So kind of saying, oh, these cycles I have to
As soon as you're
glue
dealing,
together and shrink accordingly such that I can realize these types.
I mean, as soon as you're dealing with Calabi-Yau threefolds, you have this for 1111 already, this 4-dimensional period, right? The maximal dimensional variations are 1-dimensional. Only countably many of these can happen in geometry. We don't know exactly which ones.
Anyone?
With the math.